Hello everybody, in this lecture I would like to provide a combinatorial proof of Wilson's theorem. Here is the statement of the theorem. If P is a prime, then P divides P minus 1 factorial plus 1. We can also express this in the language of modular arithmetic. So therefore you can simply express this as P minus 1 factorial is congruent to minus 1 mod P. Now it's very easy to prove it. When P is equal to 2, we get that 2 minus 1 factorial, which is just equal to 1, is congruent to minus 1 mod 2, which is true. So for the rest of this video lecture, I will assume that P is greater than or equal to 3, an odd prime. Okay, so how to proceed? Simply consider a regular p-gon. When I say a regular p-gon, you can simply consider a circle with p points on it. So 1, 2, 3, and so on. P minus 1, p minus 1 over 2, p plus 1 over 2, and then how many polygons can we form by joining these points, right? And all the points will have to be connected to each other, so you are not allowed to raise your hand in that sense. We call these polygons stellated p-gons, but I guess it is clear what we mean. For instance, in the case of 3, there's only one way, and you do this. That's it. So the more interesting case is when P is equal to 5, and then it will also give us a clue on the generalization. So let's consider the case P is equal to 5 for now. P is equal to 5, and let's see how many different ways we can create this stellated p-gon. So we have our picture here. Well, one way to go, 1, 2, 3, 4, 5. So one way to go would be to do, well, why not? So we can just draw the regular pentagon, right? That's one way. Another way would be, let's draw it. Another way would be to 1, 2, 3, 4, 5. You can start from 1 and you can jump 2 by 2. So 3, 5, 2, 4, and 1. Again, you can think of these as pointed stars, right? So, but we call these shapes as regular stellated p-gons. So because the shape is the same up to rotations, there's only a unique one of this one and a unique one of this. So these are regular stellated p-gons. But now we should have other stellated 5-gons, I should say, sorry for that. We should have some other ones. Yes, of course we do. Like this, 1, 2, 3, 4, 5. So we can start from 1. Oops, yeah. So we start at 1. And we can go to its two neighbors, 2 and 5. But instead of 5 going to 4, 5 can go to 3, 3 to 4, 4 to 2. And that's also a legit stellated 5-gon. What's interesting about this one is that we can rotate this shape 5 times, right? So, and in each case, we would have a similar shape. So this can be rotated in 5 different ways. But then this also inspires us on another one. So we can also, when you think about it, 1, 2, 3, 4, 5, there's only one other way to do it. And instead of 1 going to 2 and 5, it can go to 3 and 4, and then like, no, not like that. Sorry for that. Yeah, so 3 is going to 2. Sorry for that. 3 is going to go to 2, 4 is going to 5, and then like this. Yes. And then again, you can rotate it in 5 different ways. Only up to rotations. Consider only up to rotations. Well, actually, it doesn't matter. You can reflect it too if you want to. But okay, so the idea is clear, right? So in total, we have 1 plus 1 plus 5 plus 5, 12 different ways to draw the case for p is equal to 5. So, but why 12? The idea is very simple. So 12 is simply equal to 5 factorial. There's 5 factorial ways we can describe each one, right? However, we can start the description from any point, so up to rotation. So there are 5 different ways to rotate it. And then once I start describing it, let's say that my starting vertex is 1. There's 2 different ways I can go, 2 or 5. So I need to further divide it by 2. And by the way, this is nothing but Burnside's lemma, and that's why I have listed it here under the Burnside. So basically what's going on here is we have a group symmetry here. The group members have 5 rotations and 5 reflections for a total of 10. So the formula would be 1 over 10 times the fix of each of the symmetries. But then because each one of these vertices have a different name, so as a result, the only one which is legit is the identity one, which is just 5 factorial. So that's the answer, 12 again. But anyhow, so even without knowledge of Burnside, this is a good way to do. But then well, because of the rotational symmetries, I would be very interested in splitting this count into 2 parts. So 2 of the shapes were regular, and the regular ones, they are just unique. They are totally symmetric, So so it's the same shape in that case, right? So how many of them are regular stellated p-gons, and how many of them are just non-regular, irregular stellated p-gons? So for instance, if you consider the case for instance, if you consider the case p is equal to 13, you would just realize that we would have I believe it should be six different regular stellated 13 gone, and these shapes are, well, do I have space? Yeah, why not? Let's quickly do it. 1 2 3 4 5 6. Okay, so you start from 1 shoot 13 10 I need 5 more. 1 2 3 4 5. 1 2 3 4 5. Okay, 1 2 3 4 5 6 7 8 9 10 11 12 13, and I can quickly do the others. Let me finish the others and then let's go back to the video. Okay, so how does it go? How does the stars show up? Well, one way would be just the regular 13 gone like this. That's one of them. That's a regular stellated 13 gone, right? So another one would make 2 by 2 jumps. So if we start here, we go to the next guy, to the next guy, to the next guy, and so on. But luckily p is prime, right? So we go like that. Okay, so you get the idea. And we go back to the original starting point. Then you can go 3 by 3, yes. So let's go to this guy, skip 2, skip 2, skip 2, skip 2, 1 2, skip to that guy, that one, this, and finally so you guys are awesome. So and so on. Now we can skip 3, 1 2 3, skip 3. Is that right? I hope so. 1 2 3, this guy, 1 2 3, 1 2 3, 1 2, 1 2 3, this guy, 1 2 3, 1 2 3, 1 2 3, 1 2 3, 1 2 3, 1 2 3, and skip 4. So we start from here. 1 2 3 4 5, go to this guy, 1 2 3 4 5 to that guy. 1 2 3 4 5 1 2 3 4 5 1 2 3 4 5 1 2 3 4 5 that guy. 1 2 3 4 5 1 2 3 4 5 1 2 3 4 5 1 2 3 4 5 that guy, and then the remaining people, right? So this one, and finally 6. Let's start here. 1 2 3 4 5 6. Go opposite. 1 2 3 4 5 6. This guy. 1 2 3 4 5 6. This guy. 1 2 3 4 5 6. 1 2 3 4 5 6. 1 2 3 4 5 6. 1 2 3 4 5 6. 1 2 3 4 5 6. 1 2 3 6 6. 1 2 3 4 5 6 6 6. Haha, 6. So we have 6 regular stellated, 13 gons. You get the idea. In total we have 13 minus 1 over 2, which is 6. For instance, in the case of 5, we had how many regular stellated ones? We had 5 minus 1 over 2, which is 2. So basically the formula would be simply p minus 1 over 2. But now what's important is that the rest of the shapes, for instance, in the case of 5, it was divisible by 5, right? So the number of ways to there are 5 rotations. The same thing here. We will have 13 rotations here. So long story short, the number. So therefore, of the total p factorial over 2p stellated p gons, if you remove the regular stellated p gons, which is just p minus 1 over 2 of them, so the remaining ones will naturally fall into this many groups, right? Yeah, because in each group you will have, in each group we will have p elements, which you can simply obtain by a single member in that group by simply rotating it. And this one is a perfect example, right? So but you can just start with this one, and you can rotate it by 2 pi over 5, 2 times 2 pi over 5, 3 times 2 pi over 5, 4 times 2 pi over 5. So there are 5 different configurations. So the same thing here. So therefore this number is definitely divisible by p. But then we can rearrange it nicely. So the first expression will simply become p minus 1 factorial over 2. I can move it down. So we have p minus 1 factorial over 2 minus, and this guy will be 2p, sorry, 2, wait a second, 2p, and this one would be p minus 1 over 2p. So therefore we have p minus 1 factorial minus p plus 1 divided by 2p, and this is an integer, right? So that's perfect. So therefore in the language of modular arithmetic we have that right, well, without even resorting to modular arithmetic, so let's first figure this one. So p minus 1 factorial is definitely an even number, and then this guy here is also even because p was a prime greater than 2, so this guy is also even, so the whole numerator is even. Obviously it would be divisible by 2, so therefore this would imply that now for the rest should be also divisible by p, so this would imply that p minus 1 factorial, well, p is already divisible by p, so p minus 1 factorial plus 1 is definitely divisible by p, or in the language of modular arithmetic, finally you get p minus 1 factorial plus 1 is congruent to 0 mod p. Finally, this implies p minus 1 factorial is congruent to minus 1 in mod p, and this is the celebrated Wilson's theorem, and we are done. Hope you enjoyed the video. Looking forward to see you guys in our next lecture.